Hello everyone, it's our great pleasure to share our latest research findings with you. First, I need to explain what the subgridding method is. Suppose we have designed an irregular structure. If we choose to use fine meshes for calculating it, we may face the problem of low efficiency. On the other hand, if we choose to use coarse meshes, we may encounter issues such as reduced accuracy or even incorrect results. Therefore, we consider whether it is possible to use fine meshes around the small structure and coarse meshes in the outer region. This approach ensures both accuracy and efficiency, which is the basic idea of the subgridding method. The subsequent question is how to define the boundary conditions for the subgridding method. In recent years, many novel FDTD subgridding methods have been proposed. However, these methods often encounter issues such as complex formulations and cumbersome computations to varying degrees. Therefore, we aim to propose a subgridding method with simple and clear formulations that facilitate computations. Here, we introduce the proposed method. The left diagram depicts a schematic of the subgridding boundary when the grid size ratio is 3:1. Clearly, due to the truncation of the boundary, the fine grid electric field in blue needs to interact with the coarse grid magnetic field in green during computation, and vice versa. The coarse grid magnetic field in green also requires interaction with the fine grid electric field in blue during computation. Therefore, we modified the discrete finite difference form of Maxwell's curl equations, introducing two coupling matrices. Existing literature suggests that, when these two coupling matrices satisfy symmetry, the system exhibits stability. Next, we need to derive the time-marching formulations at the subgridding boundaries, which can be divided into three cases. In this video, we will only derive the formulations for case 1. Detailed explanations for the other cases can be found in our paper. We will use X9 in case 1 as an example. Firstly, the length of the coarse grid magnetic field in green is longer than that of the fine grid magnetic field in red, so it needs to be truncated in length. Here, we introduce the length cutoff coefficient. Then, we need to interpolate the coarse grid magnetic field to the correct positions to assist in the computation of the fine grid electric field. Here, we introduce the linear interpolation coefficient. Then, we can get the time-marching formulation for the fine grid electric field. Due to the utilization of the symmetry method, all coupling coefficients in the time-marching formulation for the green coarse grid magnetic field have been obtained in the previous process. Therefore, we can directly write down the formulation. This method enhances the efficiency of subgridding initialization and subsequent computations. After completing the formulations, we need to validate the algorithm. Firstly, we employed a multi-level nested subgridding structure and tried various grid size ratios. We obtained numerical results with long time stability properties across different cases. Then, we investigated the reflection coefficients of the proposed subgridding method at different grid ratios. The results indicate that the proposed method exhibits low reflection coefficients across various grid size ratios. Finally, we further demonstrated the efficiency and accuracy of our proposed method through an aircraft example. Compared to the fine grid method, the subgridding method can achieve an 11-fold improvement in efficiency while maintaining accuracy. If you have any questions, please don't hesitate to send us emails. Thank you all.